Right. So again, good morning. Welcome to the flight mechanics sessions today. Today we're going to talk about um, turns and maneuver. Um, I think I'll better skip this straight to what we're going to discuss. Obviously, as we now been into uh, is it week 9? So week for first week is when we started. What an academic year, we are already in week 17 now, I guess. So we've been in week 17 already. So we've been discussing maneuvers already for the past few weeks, starting from the level flight and then climb, glide, and then last week we discussed about the takeoff and landing. Now we could consider that maneuvers. Obviously, we didn't really talk about what actually maneuvers is. Maneuver is actually, we could consider that as well. Maneuver happens when the aircraft makes a curved trajectories with respect to the ground, and it changes the direction of airspeed. Now, the most important changes occur in the angles of. I think we have seen this already last week. If you climb, then the changes in flight path angle, which is gamma, in terms of climb angle and flight path angle or climb gradient or glide angle. And of course, now today, if you talk about turn maneuvers, then that also include with respect to the side as well, which is yaw angle. Okay. Now, obviously, I mentioned about in terms of variation of gamma or flight path angle, then maneuvers that we have already discussed the other day is the climb and glide, and hopefully we could see about what actually the pull-up maneuvers. Now, obviously, pull-up maneuvers is you could consider that as instantaneous event when you start from. Let's see if I could bring my aircraft. If I could just change slightly my. In terms of, for example, if you start from a level flight, then if you start to climb, and then that is when you say you're doing the pull-up, right? Now, obviously, that is not really like an important point of maneuver if you are talking about the commercial jet passengers like this, like what you are designing, obviously in aircraft design. But it will be a very important maneuver assessment if you would like to do it, if you are talking about the fighter aircraft, for example, because the pull-up maneuver or the pull-up maneuver capability of your aircraft, it actually determine how fast that you could, for example, intercept your enemy, or even you make a climb, or even if you talk about not only the military or fighter aircraft, I'm talking also about like an aerobatic airplane, for example, that they want to do like a complete loop, 180-degree loop. Then obviously the pull-up maneuver is one of the quite important parameters for them to consider. We're going to talk about that hopefully today, if we could. And then obviously, if you look at the rundown of our lectures, this probably may take a couple of weeks, so to this week and next week's, and hopefully we could also, before we started the static stability discussions in the week after next week, then we could start also talking about static stability later on in the in next week's session. Okay, so then obviously if we consider that as your um, um, maneuver, then obviously that pull up is also obviously quite important for you to look into rather than only climb and glide that we discussed earlier. But of course, I think climb and glide are very important because I mentioned that probably the two aspects of maneuvers that you need to assess or you need to investigate if you do your flight sim assignments when you're modeling your aircraft on X-Plane or on Merlin simulator. Now, In terms of variations of psi, sorry about that. Let's change to a pen. Not sure why it disappeared my pen. So in terms of variation of psi, then obviously that is considered about something that changes in horizontal plane of symmetry. We talk about vertical plane of symmetry. We look at the, I hope you can see me. I don't need to change it to camera now. In terms of plane of symmetry, vertical plane of symmetry, then we talk about the, well, translational motions and a pull up and climb and glide. But of course, if you look at the horizontal plane of symmetry, if you look at from the top of your aircraft, then obviously something to do with the change of your directions of flight, then obviously that consider that as like when you do a bank turn, that change your directions either to the left or to the right, or even in uncoordinated turn, which is quite unpopular, which is unprepared. If you are talking about the commercial passenger aircraft like this, then uncoordinated turn is not something that you would like to do, obviously. But of course, if you do an aerobatic airplane, again, we talk about the non-conventional aircraft like aerobatic airplane or a fighter airplane, then obviously sometimes the pilot wants to do a uncoordinated turn. We're going to look into that, what actually the uncoordinated turns here. Now, in a steady level flight, we talk about this already as well, then we always see that, if I could just draw that equation again, in steady level flight, we always see that lift equals to weight, right? But if I want to maneuver my aircraft, start from steady level flight, right? In a trim condition, for example, now, if I want to maneuver my aircraft, the question is here whether I need to make sure that, or I have to ensure that the lift is more than the weight. Otherwise, you're not going to be able to do that kind of maneuver. So now we could consider that if we want to make sure the lift equals the weight, like in steady level flight, we could then consider a factor for that, which is, we call it n in this case. So I will have to make sure that n is always there in order to make sure that my lift is always could carry or could lift off my aircraft in, which is obviously consists of its weight, right? Now, if we talk about that, sorry about that, so I should go further. That is what then comes to the term called load factor. So load factor, or N in this case, can be thought as how much the aircraft weight increases. But of course, now it's kind of like absurd to say that the aircraft weight increases, because the aircraft weight never increases during your airborne, because it's not possible to gain weight in midair. Now, but forces other than just gravity, obviously, that cause your weight, mass of your aircraft gaining weight, because of gravity are acting on your aircraft in flight. Now, those forces increase sometimes. So what kind of forces is that? Now we're talking about other forces than your weight, is obviously your hydrodynamic forces, which is your drag, your side force, or your lift, for example. Or even if you change your control surfaces, that could create also what we call it external forces, which is something that acting once you do the maneuver. So when this happens, obviously the result is a load put on your aircraft, which is greater than just the weight of the plane and whatever inside of it, which is your payloads, passengers, and all the contents of your aircraft. Now, since it's expressed as a factor, then load is shown as a ratio of the amount of lift. Now we talk about lift for the moment, because later on you will see, or you will realize that actually, although we have a load factor as a factor, so you have a component in X, you have a component in Y, you have a component in Z, but later on you will realize that actually the most significant load factor happens in Z direction. which is obviously the ratio between the lift and your weight. So now, since it is expressed as a factor, then the load is shown as a ratio of the amount of lift generated over the weight, or the apparent weight. Okay. Now, this is related directly to the amount of lift that wings needs to produce. So if I say that, usually the unit of this, obviously you can see this is not like there's no unit of that. It's because force is obviously Newton, then weight is obviously in terms of Newton. So this is, we could consider that non-dimensional, but of course, sometimes in layman term, they use a unit G, or sometimes G force. Now, usually, for example, if an aircraft pulling a 2G, then it means that it will need to make it twice as much lift to counteract the increase of the weight of your airplane. So in a normal condition, when we talk about, before we talk about a steady level flight, where lift equals to weight, when you do a steady level flight. So if lift equals to weight, and obviously the thrust equals to drag, right? In level flight, then we could consider that the load factors equals to 1, right? Because we consider that for load factor in Z axis, which is lift equals to weight. So in steady level, lift equals to weight, then obviously you could consider that NZ for level flight is 1, or we could sometimes we call it as 1G. So you're pulling 1G in a steady level flight. Now, of course, this parameter we could then put as a constraint when you design an aircraft, right? So in aerodynamics and perhaps in aircraft structure point of views, we use a visual representation, which is termed the flight envelope. Later on, we will talk about the flight envelope, which defines the operational limit for your aircraft with respect to maximum speed. Obviously, later on you will see for one flight envelope, the x-axis is your speed or your velocity, and then the load factor as your y-axis. So we could then limit what is the maximum speed of your aircraft could fly, and of course, what is the maximum load factor that it should endure in terms of, you know, limiting. For example, it is very obvious, I mentioned earlier, which is in terms of your structure. If you fly beyond the load factor, for example, then your aircraft structures will disintegrate, which is obviously is not something that you want for that. So if we could then put an envelope for your aircraft that it could fly within that envelope, then you could kind of like limit that. So to avoid that, well, obviously a structural damage or structural deformation. But most importantly, I guess, if you design a passenger aircraft, is about your human inside, which is obviously human could also suffer a certain amount of G-force. If you are talking about fighter, obviously fighter pilot is trained to do, you know, to sustain quite high G-force because they are trained to do that. They're supposed to do that in terms of maneuvering the aircraft itself. But of course, if you are talking or we are designing about your commercial passenger aircraft, now we're talking about the passenger comfort, the passenger sustainability, or human being inside, then obviously there is a limit. Then we always refer the limit of the G-force or load factor here to always to the CS25, for example. Then I will show you how or what actually CS25 says about G-force. Okay. Now, obviously, the flight envelope, I said earlier that actually the flight envelope defines the operational limits for your aircraft with respect to maximum speed and load factor, given a particular atmospheric density. Okay, so if a different atmospheric density, then usually sometimes you have a slightly different load or flight envelope. But of course, Now, as an aircraft designer, usually you use, the x-axis, which is the velocity. You use equivalent airspeed that could also apply to any different atmospheric density. Okay, let's have a look. If we go to the next slide, which is I'm going to go back and forth between this slide and the next slide. So we talk about visual representation here. So there are, I think, two main aircraft flight envelope diagrams that you will encounter, but I'm not sure we have time to look into the other one. Normally, these diagrams depicting the relation between one flight parameters with the other. We talk about already between velocity and load factor, because the other one include airspeed as well, normally expressed in Mach number, and then flight altitude variation. So there are two representation. One is your VN diagram, which we're going to look at later on. I'm not sure why I always disappear the pen. The VN diagram, but as I mentioned about there is another one which is VH between your velocity and H, which is the altitude. We call it like a cat paw because the diagram, it looks like a paw, but if you click through the books, you will see how it looks like. It more or less like something like this is the V, this is the H. Sometimes, as I said, represented by Mach number. The diagram is more looks like that, I guess. So you are allowed, your aircraft obviously allowed to operate within this speed and within this altitude, for example. Now, sometimes if people wants to compare the maneuverability of two fighters, for example, that could, overlay to flight envelope, for example, between F-16 and say MiG-25 or MiG-29, you will see that there is, for example, like a different aircraft. If I could just draw a different color, perhaps, just to show you. If this is belong to F-16, the red one, and if you superimpose, say, or MiG-25 or MiG-29, MiG-27, whatever the Russian airplane is, and you will see there is some, for example, superiority of one aircraft to the others, or vice versa. So you will see that there is the maneuverability or capability of aircraft which is superior than the other. Okay. Now, if we look at the VN diagram, so let's ignore this for a moment. We are going to look at this flight envelope, which is VN diagram. If you look at that, sorry, I always put the next. This is how it looks like. So the x-axis is obviously your airspeed. In this case, indicated airspeed, as I mentioned. If you want to kind of like mostly apply it for your any atmospheric density, usually people use this or draw this using equivalent airspeed rather than indicated airspeed. Okay, so the x-axis is your airspeed, V, and obviously the y-axis is your N. So now, if you look at here, I think we established that. Now, there are several limits. If you look at the VN diagram, there are several limits of your aircraft that you could actually indicate. The first is obviously your aerodynamic limit. Then that's something to do with the capability of your wing to produce the lift itself. Now, obviously, in terms of the speed, there is a minimum speed that your aircraft could be with relate or with respect to the CL, the maximum CL that your aircraft could produce. Now, I believe that you have seen this a few times already, which is the equation for the speed, which is a square root of 2 times W, or weight, aircraft weight, divided by rho as CL. Now, obviously, if you want to consider the minimum speed or stall speed before your aircraft due to stall, then obviously I always draw that in the class. This is your alpha, CL alpha curve, for example, and then some typical one looks like that. Then before your aircraft stall, you could reach your CL at CL maximum at that point, for example. then before it stall. Now the speed that could be at that point is obviously we call it a stall speed before aircraft reach beyond that or below that your aircraft could stall. That could be expressed in this equation, which is 2 times your aircraft weight divided by rho as CL max. Now, that minimum flight velocity depends on obviously the wing loading. As you can see, that is your wing loading there. So the bigger of the wing loading, the bigger of your stall speed, obviously. But of course, if you want your aircraft able to fly a very low velocity before it stalls, then obviously your wing loading should be a bit smaller, right? So that is quite the opposite of what we try to optimize during cruise flight, for example. Now, if you look at that diagram, obviously, if you fly in straight level flight where lift equals the weight, where your ends equals 1, right? 1g, then this is 1g, obviously. Now, obviously, that is where your stall speed happens, right? So if you draw that, that is your v stall, right? Now, of course, from this equation, if you want to consider as v as the functions or the velocity as the functions of the n. Now, if I could redraw or rewrite your equation here, you could consider that Vs square is 2 times, n, which is your load factor in here, times W, and times rho, times S, times CL max. You agree with that? If the n equals 1 in a steady level flight, then you have your V stall, which is this one. Okay, but if you increase the speed, right, then you then increase the n as well. You follow? That if you draw that in a graph, right, this equation, which is n, if you could rearrange that and n as the functions of your speed, right, or v stall in this case, then you have a graph like that. So if you start from 0, it goes up to all the way up. Sorry, if I could just draw that like that. Okay. Now, of course, it has to stop somewhere, right? First of all, I've talked about structural damage. Then there is a condition where your structure could sustain. In this case, for example, in this very example, when the n or the g force at g, 4 point something, maybe 4.4 here. But then if you fly beyond that, then obviously your structure start to have a deformation. At some point, it will then disintegrate. I think is that g force or n equals 6.5, perhaps, that in these examples. Okay, but of course, there is, as I said, there is a limit more important than this structural, obviously, which is your human being who fly the aircraft. Obviously, your human being is only sustained, I think, beyond below 4.4 in this case, and sometimes it's just about 2.5 or between 2.5 to 3 point something, which is actually is defined in your CS25. I could just pull up CS25 quite quickly just to show you some paragraph shows that. This is what CS25 says about your aircraft, which is CS25 is the document that you use in your aircraft design. For example, the positive limit maneuvering load or a load factor, sorry, n for any speed up to VD. We talk about VD later on, which is VD is your dive speed, may not less than 2.1 plus 24. So there is a limit in there, which is about 24.00, which is W is your aircraft weight. Sorry about that. And then plus 10,000 feet. Except the n may not be less than 2.5 and it need not be greater than 3.8 Okay, so the maximum that you could put for your Venn diagram is 3.8, but of course it should not be less than 2.1. So when you design the aircraft, your aircraft should sustain at least 2.1 plus the weight of your aircraft following this expression. Now remember, if you use this, which I expect that you could draw this for your aircraft design, but we're not talking about aircraft design here. Later on, you could produce your Venn diagram for your aircraft design. But of course, if you use this limit for the top n factors of your Venn diagram, remember that it's using the unit of weight in pounds. So if you happen to work with Newton, for example, then you have to convert that into pound, and then you could use this, and then you could put up the maximum load factors of your aircraft. Okay, so let's go back to the slide. So that is the maximum then. So if you're talking about that, following the CS25, as I said, your upper limit might be start from there rather than over there, right? So now later on, you will consider how much is your structural damage. Depends on the structures or the materials that you use. Okay, but of course, if you look at this Venn diagram, then you have how do you call it, several points that you might find it's quite important. The first is obviously this point, where if you fly in steady level flight, G equals 1, you have a point where your aircraft should not. That is the line when when you do a level flight at 1G, right, or 1G force. Now, the minimum speed that you are allowed to fly is obviously that corner there, that point there. Because if you fly below that speed, then obviously you're going to have stall of your aircraft. Okay. Of course, if you increase the speed, to sustain a 1G, you will be in that point, for example, but you are able to pull up or to do some maneuver with the maximum point of your G-force is up there, and obviously later on you will find that your minimum G-force is down there. Okay, now that is the first point that you find quite important. But of course, if you talk about the point that limit the maximum G-force, which is say point B, let's call it this point B, for example. I better use the red because obviously it's not very clear in that. So if you talk about point B there, then obviously that point is, sometimes people call it a corner point or a corner speed, which is the limit of load factor and the maximum lift that your aircraft should fly. So if you are flying in this speed, I don't know, in this example, I think that speed is about 130 something. Is it somewhere there, right? This is 130 there. So 135, for example, or 136 with the load factors of 4.4. That is the corner speed, we call it, or the maneuver speed that your aircraft could do. So at the lower speed, if you go at a lower speed, go to the left, for example, the structure cannot be overstressed, and your aircraft will stall before reaching limit load factor. So between this speed and that speed, you have that limit over there. Okay, if you fly in that speed to the left, then obviously your aircraft will stall. But if you fly with a load factor beyond that, then say in this case, obviously your human being inside, which is your pilot and maybe the passengers as well, if you carry passengers, will not sustain that G-force. Okay, but if you go along that speed, then you have a constant limit load factor. Then again, the same thing, that if you fly in that speed, but of course you're not allowed to go beyond that before your aircraft structures become to have a deformation. If you even go beyond that, then is when your aircraft structures of your aircraft becomes disintegrate, and then obviously you're gonna have a structural failure. Now, this is the in this point here, obviously this is the point. Sorry, this is the point where your aircraft maximum cruise speed for your structures. Of course, sometimes people is a dangerous zone here, because if you fly beyond that speed, then your aircraft start to have a buffeting, start to vibrate, and so on. And if you keep going with a certain speed, then obviously you got, for example, if you fly going into supersonics, you're going to have wave drag and so on. That also could damage your structures as well. So now sometimes we could consider as we call it maximum structure cruise speed. To avoid that things to happen, usually we have kind of like a factor. People use it as 1.25. So if you put that like Mach 0.78 for your, or maybe this is your cruise speed somewhere there, but obviously the maximum structure cruise speed is maybe 0.85 or 86. Then you multiply that with 1.25, then that is your maximum structure failure. Beyond that, then the structure failures could happen, which is your aircraft will disintegrate. Okay, now if the aircraft operate in that region, which is the structure failure region, the red colors there, is obviously an acceptable permanence or maybe deformation of your primary structures. And then obviously, even if you sustain like a few minutes in there, then if you land, your structure need to be thoroughly checked in terms of high grade of fatigue, for example, and may take obviously the internal damage. If your aircraft is composite, for example, then internal damage may happen as well. So operations above the limit load, obviously in this red zone here, must therefore be avoided at all costs in normal operations, obviously. Okay, right. So I hope that is slightly give you some idea. As I said, as an aircraft designer, you must be able to draw this flight envelope for your aircraft with all the information about your aircraft weight, for example, your stall speed, your CL max. Now, in terms of the maximum load factors, we refer to CS25, but of course, there is a minimum load factors that you could also consider in here. If we go back to CS25 again, that is, I think, if you look at the here, it says the negative limit factoring load. Limit factor maneuvering load factor may not be less than -1. So that is the minimum that you could draw in your PN diagram. Okay, let's continue to the next slide. Then disappear. Obviously, that is a standard VN diagram in a normal flight, but of course, sometimes your aircraft how do you call it, suffer from a gas, a turbulence, a disturbance during your flight. So now what you could do is actually superimpose your VN diagram with the wind gas load as well. So if you go back to the CS25, there is also a maximum gas load that you could consider in order to add to your VN diagram, apart from the VN diagram, a normal standard VN diagram that we have seen before. If you consider if there is an atmospheric turbulence, which you should, because you always not experience the normal flight all the time. Sometimes you got a disturbance like a wind gust. Now you have to also consider this gas load, we call it. Most serious one is obviously the vertical gas. If you look at CS25, that it's talking about, the CS25 talk about the vertical gas, sorry, quite a lot, then that is need to be included in your standard VN diagram. Now, this is a very crude equation about that, which is obviously your load factor need to be added with this factor. But of course, if you refer to CS25, sorry, there's a quite complete equation that you could follow in the CS25. I think let's go back to that CS25 again, just to show you what actually it says about gas load, which is, I think, yeah, I highlighted here, so you can if you look at my cursor there, that is when CS25 says about the gas velocity applied. So the gas velocity maximum is about 17.07 meter per second if you are in sea level there. But the reference gas velocity may be reduced linearly from that values if you are flying going up to 15,000 feet. But if you go further up to 60,000 feet, then that gas, vertical gas, that you could consider that also cut into half as well. So if you use that as your guide in order to draw your gas load, then obviously you could superimpose that. So if I could just move to the next slide, so you could see that is a standard. Okay, that is the standard one that we draw before, right? So if you follow that, there's a point A, point D, point E, point F, point G, and go back to here. That is your standard before. This is limit by V-stall. Remember that you're not able to fly below V-stall or less than V-stall. Then your load factor, or sort of VN diagram, initially in the form like that, right? But adding the gas load, then following the equations that we've seen before, which is quite simple. But if you look at the CS25, there's another equation that consider the weight and the gas factor as well. Then you should be able to draw this line, positive gas line to point C and positive gas line to point D there. So then if you superimpose those lines with the VN diagram that you have, then in fact your VN diagram becomes like that. So that is the maximum that your aircraft could fly. That, of course, now the gas load here is within the VN diagram earlier. So what you take is actually the outside boundaries that your VN diagram actually put earlier before. Okay. So as I said, we're going to talk about that in tutorial. Hopefully there is, I think I remember there is questions about this, and we're going to talk about this further in the tutorial. But as I said, if you are a designer, aircraft design, you should be able to draw a VN diagram for your aircraft, considering your aerodynamics, considering your well, CS25, the standard, and obviously considering your maximum cruise speed, which will break out or disintegrate your structures. Okay, right. So now, if you look at the equation of motion, obviously in terms of velocity factors, we know that the velocity factors, if you have a climb or glide, last time we discussed about the velocity factors will make an angle of gamma, which is your flight path angle. But now if you talk about yaw as well, then your velocity factor also changes with size as well, or your heading angle, right? Now we'll go further to look at the diagrams, vertical and horizontal equation of motion diagrams. I think you have seen this before. So lift equals to weight, but of course, if you make a pull up like this, you have a flight path angle gamma there, which is also there, right? So which is, I think if I draw that like that, which is also there, right? So now the L, which is your lift, the component in there, which is this one, which is L cos, sorry, this should not be alpha, why I put alpha there, then L cos gamma, right? Sorry, cos gamma, which is equals weight, if you look at in Z axis there, right? and then D, which is your drag, equals thrust in terms of force. But of course, if you're talking about the Newton law, then you have this factor here, which is mv d gamma dt, which is obviously coming from mv square divided by r, I guess, which is your centrifugal or centripetal forces. Now we know that if you're talking about gamma dot, which is v over r, so you could also consider that v mv d gamma dt. Okay, now in terms of x-axis, we talked about that already, t minus d, but of course you have this component, which is u, which is your weight sine gamma, right? That is your sigma f, right? So if you put it in the Newton equations there, you got this m dv dt, which is your acceleration. dv dt is your accelerations. Now, if you look at the horizontal plane, it looks slightly different. If you look at here, you have a side force. If you make a turn, you have a side force S, right? So if you look at a bang angle here, if I draw again a bang angle, obviously here, right? Sorry, over there, right? That is obviously, you could consider that into the equations. If I go back to that equation, which is L cos pi, which is, again, this is pi, right? So if this is L cos pi, right, this one, and then sine minus S sine pi, which is that one, right? And it will equal, it's equal to weight cos gamma. Now in this case, we assume that gamma if your aircraft not only bang, but it's also going up like that, then you have a cos gamma. But if you consider that is only make a normal bang angle without gamma, then obviously cos gamma equals 0, then cos gamma equals 1. So you have only one particular weight component which is weight or W here. So you could consider that as L cos gamma minus S sine gamma, which is equals to which is minus W, minus the weight, is mv d gamma dt. But of course now this is exactly what we have up there, right? And then this is, if you look at the z-axis component, then y-axis component, not z-axis, then that is what you have there. So L sine gamma, which is this one, then minus S cos, L cos pi, not cos gamma, L sine pi, because this is pi, right? So this is the L sine pi minus S cos pi. Then if you look at into that equation, it equals mv d psi dt. Okay, so that is our, how do you call it, our ammunition, say, at your disposal to then talk about the maneuvers that we're going to discuss one by one in the next few slides. For examples, obviously now if we consider like symmetric maneuvers, remember that in steady level flight, lift equals weight, then obviously thrust equals D. Then obviously if you go back to the equations, then you will find out that where nz equals or the load factors equals 1. But of course, we talk about this already in climb. When you do the climb, lift equals W cos gamma. And then in x-axis, T minus D, which is equals W sine gamma. Then of course, now you can see that if you look at this, the first equation there, if we define lift equals weight is N, then obviously then N obviously will be equals to cos gamma. Then that is always less than 1, as you can see, because cos gamma flight path angles varies between from 0 to say 90 degree, right? If you look at the cos gamma functions, if this is gamma and this is cos gamma, from 0 to 90 degree is always goes like that, which is this one is 1. So whatever the gamma that you pull, then the cos gamma is always less than 1, because the cos gamma function just goes like that. You follow? So that is the consequences of your load factor if you do the climb, steady level, climb, for example. Now, if you do the glide, remember the glide is thrust equals 0. Then obviously that what you have from your equation of motion that we drive earlier. Okay, now let's look at the we have like about 5 minutes or so. I hope we could just at least talk about steady pull-up, because tomorrow we well, this week we, in tutorial session there's questions about this steady pull-up. Now this is what happens when you do a steady pull-up. Now remember this equation, actually we get it from this equation there, right? Which is L minus W cos gamma. If you move it around, then you got M, which is, well, MP d gamma dt before that, but we know that W is mg, and then obviously if you put the M, then obviously becomes W divided by G. That's where the W divided by G comes from. Okay, now we know that gamma dot, the change of gamma in this case, is obviously the speed of the aircraft divided by r. So I hope you've seen this equation way long before, which is angular rate is the speed divided by the radius of the turn. Right. So if you change this d gamma dt, which is gamma dot, obviously, then you will have these equations there. Okay. Now we go to the other equation, which is the second equation. If I go back slightly, this one, then then that's sorry about that. Then that's where the your L sine gamma, where is this equations there? Then you have the equations over there. Okay. Now, what actually could tell you in this regard, but obviously from that, the first equations there, right? So if you look at that a steady pull-up, then you can consider L divided by W is your NZ. So from that equations, remember that we have W there. If you divide it by W, obviously it becomes, well, it will disappear. But of course, the second term, which is this term, becomes that terms, right? And then you have these equations as your load factor equation. Now, what actually tells you here, obviously, if you have a gamma increase, then cos gamma becomes less than 1, but your load factor will increase if your aircraft pulling more speed, right? Or at the same time, if your R becomes smaller. Now, obviously, if you're doing a pull-up like that, then your aircraft, the radius of the pull-up, if it's smaller, then obviously you increase your G force or your load factor. Okay, so if you want to make it like a standard pull-up, then you have at least the radius of that is big enough in order not to pull the quite reasonable G force in your maneuver. Okay, now in terms of pitch rate, remember when you do the pull-up, as I said, instantaneous incidents when you try to change your flight path angle, that related to the pitch rate, you know, how much pitch rate that you want to your aircraft sustain, then that pitch rate, obviously from this the second equations, where Q is equals gamma dot, then that pitch rate could be expressed in this equation. So if you want to have a reasonable load factor, then you need to, for example, if you want to say like 1.2 with the climb, say gamma equals 10 degree, then you should make a turn no more than or bigger than this value of Q, where your V is your aircraft speed, G is your gravity acceleration. Okay. Now, obviously, pitch rate variations. This is the one that your pilot should pull rather than pull slightly or abruptly or joystick, for example. That makes your pitch rates quite high. If your pitch rate quite high, then you will have load factor or G force is quite high as well. Usually, the first what your pilot will do is actually increase the angle of attack to produce a necessary lift. And then after that, it will then goes with the what is it called, the thrust to increase the speed in order to make the Q is slightly smaller. Because if you want to increase the well, if you want to reduce the Q, not to abruptly change the flight path of your aircraft, then you could increase the V. Increasing the V, then you may do it by increasing the T, right? So I hope that is quite understandable in the way that doing the maneuver in order for your aircraft to pull up. Now, if we talk about the how much the velocity needed for you to do the pull up, you could evaluate from these equations. Obviously, this is obviously the lift, right? So if you remember this, half rho v square rho s v square cl is the lift. From that, the first equations, then you could rearrange that to get your v, which is how much velocity of your aircraft need to do. Then in these equations, you can consider also what is the if you rearrange the equations, you can then know exactly what is the R or the radius of the turn or a pull-up that you need to do in order to keep the load factors acceptable. Okay, so you remember the smaller R, the bigger load factor, right, from the previous equation. So in order to make it a sustainable pull-up, R should be no less than, or should be greater than, in other words, than these values over here. Okay, so I hope that is something that we could then talk tomorrow, or well, not tomorrow, this week during the tutorial when you do your pull-up questions. I think that yeah, before we talk about the turns. Okay, any questions for that? No. I started thinking that my voice is not really heard because no one really responds. But I hope I spend